Thanks. So I'm going to talk about simple mechanisms for both an additive and sub-additive buyer, and this is based on two works. The first one joint with Moshe, Nicole, and Brendan, and the second one with Aviad. So I'm just going to jump right into the model since we just saw a talk on a similar one earlier. So there's going to be one seller, and in this talk, just one additive buyer, so not many buyers. And the additive buyer is going to be interested in these n different items that the seller has for sale. The buyer is going to be additive for the first portion of the talk. And so that means that the buyer has a value, vi, for item I, and his value for a set of items just sums his value for every item in that set. The buyer is going to be risk neutral and quasi-linear, which just means that his utility for receiving a random set and paying a random price is just his expected value minus the expected price he pays. And similar to what we saw in the earlier talk, the seller is unsure of the buyer's values exactly, but he has this Bayesian prior. That prior is going to be a product distribution. So the seller is going to have a one-dimensional distribution on the buyer's value for each item. And that product distribution will be his joint distribution over beliefs for the buyer's values for all items. And his goal is going to be to sell the items in a way that maximizes his expected revenue. Okay, so let me go over a couple different ways that the seller could choose to sell his items. The first is he could sell the items separately. And so what he would do here is he would just post a price, PI, on item I, and then say to the buyer, you can choose to receive any subset of items you want. If you choose to receive subset S, you have to pay me the sum of the prices for every item in that set. Okay, now the pros to using a scheme like this is that it's actually very easy for the seller to optimize over all schemes like this. And it's really trivial for the buyer to decide what he wants to purchase. He just has to visit each item and figure out, is my value larger than the price or not? Okay, what's also nice is that predicting what the buyer will do doesn't rely on risk neutrality because there's no randomization. And the buyer doesn't even need to know his values exactly. So as long as the buyer is able to make one binary comparison, then you can accurately predict what he will purchase. Okay, and of course the drawback is that restricting yourself to using a scheme like this might be suboptimal for the seller. And the last thing I'm going to say before moving on is I'm going to use the same notation as the previous talk, and I'll use Srev to denote the optimal revenue that the seller can obtain by using a scheme like this. Okay, another thing that the seller might do is he can sell all the items together in one big bundle. So what he might do is he takes all the fruits together and he says to the buyer, if you choose to pay me price P, then you can get all the fruit. If you don't, then you get nothing. Okay, and again, this has the same pros as selling separately, that it's very robust. And it has the same cons in that it might be suboptimal for the seller to restrict himself to using a selling scheme like this. Okay, and again, just before moving on, I'm going to use this notation BREV for bundling revenue to denote the optimal revenue that the seller can obtain by using a scheme of this format. Okay, now the most general thing that the seller could choose to do is he could offer a lottery system to the buyer. Okay, so here what I mean is that the seller is going to post the following possibly infinitely long menu, where in this example, the first option says to the buyer, if you pay me P1, then you can get the apple. If you pay me P2, you can get the orange and the bananas. If you pay me P3, then you get the apple with probability 1/2, and you get the bananas with probability 1. If you pay me P4, you get the orange with probability 1/2, the apple with probability 3/4, and the bananas with probability 1/4. And you could have an infinitely long list with different probability vectors for the items, and a different price for each. Okay, so the upside of using a scheme like this is that it is in fact optimal over all possible mechanisms and protocols that the seller could use. So that's good. The downside is that this is a hard problem for the seller to optimize. So if he wants to find the optimal lottery system, he would have to write an LP that's a polynomial in the support of the buyer's value distribution. It's now not hard for the buyer to optimize, but it is at least annoying for the buyer to figure out what he wants to purchase, because he actually has to visit every option on the menu. He has to compute his expected value and subtract the price and see what's the largest. And because we're using randomization, being able to predict what the buyer will purchase actually relies heavily on this risk neutrality assumption. And if we got that wrong, then maybe the revenue that we predict we'll get here will be way off. Okay, and again, before moving on, the notation I'm going to use to denote the revenue of the optimal mechanism is Rev. Okay, Okay, so what's the point of going through this? So what we'd like to do is we'd really like to sell items separately or together because of these great robustness properties that they have. But what we really don't want to do is to sacrifice revenue in the event that we did get the model right and it would have been okay to use a lottery system. Okay, and really quickly, I'm not going to go through all of these examples, but I want to state that there's actually a lot of formal barriers to trying and accomplishing this. So the first one is that we know from this work of Hart and Nissan from 2012 that there are examples where selling separately can only guarantee you a logarithmic factor of the optimal revenue, and there are also examples where selling together can only guarantee you a linear factor of the optimal revenue. So for both of them, there are examples where they can be very bad. Second is we know from, this is just a sample of works, there's a lot more works actually that provide different examples, that the optimal mechanism, even in very simple instances where say you have one buyer, 2 items, and each of these distributions just has support 2, then sometimes the optimal mechanism, even in these instances, can be randomized. And there's also a series of papers that shows that if these distributions are not independent, then actually there can be an infinite gap between the revenue of the best randomized mechanism and the revenue of the best deterministic one. So randomization can become essential to getting revenue. Okay, and the last challenge is there's this really weird phenomenon called non-monotonicity, where the following thing can happen. So maybe you start with a distribution over, a product distribution over values for 2 items, and then you go through some advertising campaign and you make everyone in the population like both of your items strictly more than they did before. And now it can be the case that the optimal mechanism for this new distribution has worse revenue than the distribution you started with. And it's really bizarre that this can happen, but it can. Okay? So basically, I just wanted to highlight that there are some formal barriers to this, and that's why this has been kind of a challenging problem for a while. But there is still some positive results. And what we heard about this a little bit earlier was that Li and Yao were able to show that Srev actually is able to guarantee something. It can at least guarantee you a log n approximation to the optimal revenue. And if all the distributions are IID, then Brev does get you a constant factor. Okay, and both of these improved the bounds that were given in Hart and Nissan by a log n factor, and because of the lower bounds on the previous slide, they're asymptotically tight. Okay, and something we didn't hear about earlier, but there is work by Kai and Huang that showed if you're not so concerned about structure, but you just want to be able to find a good mechanism, whatever it is, there is a p-TAS if all of the distributions have the monotone hazard rate condition. Okay, so now I want to move into our result. So we did hear this stated earlier, but what we're able to show is that even though neither selling separately nor selling together can get you a constant factor approximation, that for every distribution, the better of selling separately or selling together does get you a 6 approximation. Okay, and so what I'm going to do for like the next 10 minutes or so is try and give you a pretty high-level overview of what the proof of this looks like. And then what I'm going to do at the end of the talk is state a little bit about the second result I wanted to talk about, which is that in joint work with Aviad, we're able to extend this result to a setting where the buyer has combinatorial valuations over the items, that is sub-additive. So here he might have values that are, depend on exactly which set of items he gets. Okay, and but I'm not going to give you a formal statement now, and I'll overview kind of why these settings are very different later as well. Okay, but now I want to get into a proof overview of the first result. So the first thing we want to look at is, okay, so what are the examples where selling separately is a bad idea? Okay, and so this example is from Hart and Nissan's paper. And so the bad example is if the buyer's valuation for every item is drawn independently from what's called the equal revenue distribution. So this is a distribution such that the probability that the buyer's value exceeds x is exactly 1 over x for all x in all items. Okay, so it turns out that for this distribution, maybe it should be easy to see that if you sell separately, you're going to get revenue exactly n, because you're going to get 1 per item. No matter what price you set for each item, if you set price x, it's going to sell with probability 1 over x, so you get revenue 1 per item. But it turns out that the sum of values concentrates pretty tightly around n log n for these distributions. Okay, so what does that mean? That means that something you can do is you can set a price equal to n log n over 2, and then the buyer will choose to purchase this with pretty high probability, and so Brev is something like n log n. Okay, so this means that, so this is an example that shows that Srev can't guarantee better than a log n approximation. And the takeaway from this is that Srev, it seems like, is bad whenever the sum of values concentrates. Okay, but we can note that Brev is at least good in this case. Okay, now we can say, so when is Brev bad? So here's an example also from Hard and Nissan, where the value for the items are going to be like wildly asymmetric distributions. So here the distribution of values for the jth item, the buyer's value is going to be 2 to the j with probability 2 to the minus j and 0 otherwise. Okay, so now maybe we can see that if you choose to sell all the items together in one bundle, there's no way to get revenue larger than 2. And this is because for whatever price you choose to set, the probability that the sum of values exceeds it is at most 2 over x. And I'm not going to go slowly through the math, but this is by taking a union bound and then observing that this is a geometric sum. Okay, but we can still see that if we had just sold each item separately at price 2 to the j, we'd go back to getting revenue 1 per item, which would be n in total. Okay, so what that means is that Brev can't guarantee you better than n approximation on every distribution. Okay, so what we learn here is that Brev is bad when all items contribute evenly, but they're on these wildly different scales. And it turns out that in this case, Srev happens to be good because basically many of the items are 0 with high probability, and when there are very few items to deal with, Srev is okay. Okay, so the intuition that we gain from these examples are that Brev is good when the sum of values concentrates. Srev seems to be good when most item values are very small compared to the rest. And so we can ask, does every distribution fall into one of these two categories where either Srev is good or Brev is good? Okay, and the answer is not exactly, but we can still use this intuition to guide the analysis. So formally what we want to do is we want to use this idea called the Quartal Decomposition that was introduced in Li and Yao's paper to prove their results. And so what we're going to do is for each item, we're going to split the support for that item into what we'll call the core and the tail. Okay, and the tail is what you would expect. We're going to pick some cutoff, and we're going to say everything that exceeds this cutoff we'll call the tail, and everything that's below this cutoff we'll call the core. Okay, and the cutoff we're going to choose for every item is going to be exactly Srev. Okay, so now we can talk about for an item, we can say your value for that item is in the core if your value for that item is small, and your value for that item is in the tail if your value for that item is large. And I'm also going to define some terms. So I want to say if I give you an entire valuation vector, yes?
The cutoff for item I is
The total Srev, that's right. So it's going to be a very high cutoff. Yeah. So I also want to say an entire valuation vector is in the core if every item is in the core. So if your value for every item is small. And I'll say that valuation vector is in the tail if your value for at least one item is large. And like Malesh pointed out, this is very large. It's larger than Srev for selling all the items together. Okay. So from here, at a high level, there are 3 steps to completing the proof. The first step is we prove something called the Quartal Decomposition lemma. And this is a little bit of an informal statement of what that lemma says. What it says is that the optimal revenue for any distribution is upper bounded by the total welfare, so the expected sum of values for that distribution, conditioned on the values being small, plus the best revenue that you can get from that distribution, conditioned on the values being large, at least one of the values being large or in the tail. Okay, so once we have this decomposition lemma, we just need to show that Srev and Brev can get a constant factor approximation of each term separately. So bounding the tail, it turns out that the revenue that you get from the tail is upper bounded by 2 times Srev. And I'm going to completely skip saying anything more about the proof of this. But basically what's going on is that we said that these cutoffs are really, really large. And it turns out that they are so large that we're unlikely to see more than one item in the tail at the same time. And so you should see if there's only one item to deal with, then selling separately is the same thing as doing the optimal mechanism. And if there's more items in the tail but not many, then it degrades not so poorly. Okay, so that's all I'm going to say about that. But basically, because the cutoffs are large, Srev does well on the revenue from the tail. And the last step is we have to show that Srev or Brev can obtain a constant factor of the welfare from the core. Okay, so here the idea is that maybe the welfare of the core is less than 4 Srev. If that happens, then great, we're in good shape, and Srev gets you a constant factor approximation. If that doesn't happen, so what's going on? We said that our cutoffs were exactly Srev. So that means we have a bunch of independent random variables that are each bounded above by Srev, and the expected sum of these random variables is larger than 4 Srev. Okay, and it turns out that this is actually enough information to show that the welfare of the core must concentrate. Okay, and when the welfare of the core concentrates, we can use the same trick we saw in the example and just set a price equal to like half of the welfare of the core, and then with good probability, the buyer's values will be above this and he'll choose to purchase, so Brev gets you a constant factor there. Okay, so what I'm going to do now is I'm going to give you kind of a sample of the small lemmas that go into the one lemma that goes into the proof of step 1 and one lemma that goes into the proof of step 3. So it's not going to be like a chain of events that will lead to proofs of these, but I just want to give you a sample of what the proofs look like. Okay, so one of the key lemmas that goes into this core decomposition lemma is what's called the Marginal Mechanismlemma, and it appeared in Kai and Huang's work and also Hart and Nissan. So it's not our lemma, but I think it's a good sample of the kind of techniques that go into proving this. Okay, and so what this lemma says is that if you have two disjoint sets of items, and I have a distribution over values for one and a distribution over values for the other, and they're both additive, then what's not necessarily true is that the revenue of selling all the items together is upper bounded by the revenue of selling them separately. But what is true is that the revenue of selling both together is upper bounded by the welfare of one set of items plus the revenue of the second set of items. Okay, and I think actually I'm going a little slower than I thought, so maybe I'm going to skip this proof, but I'll talk a little bit while it's on the slide if you want to try and read it quickly. So basically what's going on, all I want to say that's important about this proof is we're going to come up with some trick that says if I know exactly how much value you get by adding items in S to whatever items in T you get, then I'm just going to try and pay you back for these items instead in a mechanism that used to sell both items, and now I'll only sell the items in T, and I'll just like buy back the items in S from you. Okay, so at a really high level, that's what's going on here, and yeah, so I'm sorry for going through that quickly. Okay, so now for the analysis of the core, I think I'll also go through this a little quickly. So here's just a quick observation that is going to be helpful for what's coming next, is that for all items, I, and for all x, the probability that your value exceeds x is certainly upper bounded by the revenue from selling that item by itself over x. So why is this? If this was false, then I could offer item I at a price of x, and I would definitely get revenue that's strictly larger than the revenue of di, which would contradict the definition of the revenue of di. Okay, and it turns out that this observation alone is enough for us to bound the variance of your value for item I conditioned on being in the core. Okay, and it turns out that it's upper bounded by 2 times Srev times the revenue of selling just item I separately. And so really all that's going on is this is a chain of inequalities, and the last step is just going to be evaluating this integral. So maybe if you want to try and go through that, I'll leave it up there, but I won't go through it slowly. Okay, and so as a corollary of this lemma, we can show that the variance of your value, your sum of values for all items conditioned on being in the core, is upper bounded by 2 Srev squared. So why is this? Well, D is a product distribution, so variance is additive across the variance of its components. Here's a bound of the variance of its components, so when I sum this over all I, this last sum turns into exactly Srev, and that's where the 2 Srev squared comes from. Okay, so once we have this corollary, now we have to look at two cases, and this is like what we said before. One thing that might happen is that the expected welfare condition on being in the core is upper bounded by 4 Srev. If this happens, then clearly the better of Srev and Brev gets you a 4 approximation to this. If this doesn't happen, then Chebyshev's inequality says that the sum of values conditioned on being in the core concentrates. So why is that? Because the expected sum of values is larger than 4 Srev. The standard deviation is less than root 2 Srev. And so just directly plugging into Chebyshev's inequality says it must concentrate. So what that means is that you can sell the gram bundle at a price equal to 2/5 times the expected welfare. It will sell with probability at least 5/8. And this means that Brev will get you at least 1/4 of the welfare from the core. Okay, so just to recap what I said so far is that there were 3 steps. The first step was this Quartal Decomposition lemma, and what I wanted to highlight was that the proof used this Marginal Mechanism lemma. And what was important was that we wanted to turn a mechanism that sells items in S union T into a mechanism that just sells items in T. And we did this by basically buying back from the buyer the items in S. But to do this, we needed to know exactly the buyer's values for items in S. The second thing we did was I didn't do this, but I stated that we could upper bound the revenue from the tail with 2 Srev. And then we upper bounded the welfare of the core with 4 times the better of Srev and Brev. And again, I want to quickly highlight that this proof used the fact that Srev is additive across items, that Srev is just equal to summing over all I, the revenue of selling that item by itself. And we also use the fact that variance is additive across sums of independent random variables. Okay, but this gave the first main theorem, and so that's everything I'm going to say about this model. And now I want to move on to subadditive buyers. Okay, and so what I'm going to do is I'm just going to describe the model. After I describe the model, I'll tell you why this problem is different than the one we just saw, and then I'm just going to wrap up. Okay, so here there's still one seller with n different items for sale. There's one buyer. The buyer has a subadditive valuation for the items. So that means their value for just the apple might be this, and their value for the apple and the orange together might not necessarily be any function of his value for the apple by itself and his value for the orange by itself. Okay, the only thing I want to assume is that the value for the union of 2 sets is upper bounded by the value of each set separately. So this is what subadditive means. Okay, the seller is again unsure of the buyer's valuations, but has a Bayesian prior. So what is the prior in this case? So it's just a prior over functions. And the only restriction I want to make on these functions, we need some kind of independence assumption. The assumption I want to make is that for any disjoint sets of items, if I look at just the random variables v of S1 to v of Sk, I want these to be independent random variables. Okay, so that's the only independence assumption I want to make about the distribution. Okay, and again, there's this asterisk here because actually stating this correctly is a little bit more technical, but I don't want to go into details about this. In spirit, this is what the model should be. Okay, and again, the goal is to sell the items in a way that maximizes the seller's expected revenue. Okay, so I want to give you a couple of examples because the model is pretty abstract of some distributions that do satisfy our assumptions. So the first is maybe you have a unit demand buyer. So he has a value for each item that's drawn independently, and his value for a set of items is just his favorite item in that set. Could have a K demand buyer where he has a value for each item drawn independently, and his value for a set of items is his favorite K items in that set. You could be additive up to more complex feasibility constraints where you pick your favorite feasible set within whatever you're allocated and sum your values for every item in that set. And maybe the more interesting one is you can have fractionally subadditive or XOS valuations where you can have possible values for each item that are drawn independently but may be correlated within an item. And now your value for a set is picking the index j that maximizes your sum of values if I choose index j across all of the possible values. Okay, so it still makes sense to sell separately in this setting. So you can still post a price on each item and tell the buyer pick whatever you want. And something that's funny here is that now it's actually NP hard just for the buyer to pick his favorite set. And it's also NP hard just to compute the revenue of a fixed item pricing. Okay, so these are barriers that somehow we're going to have to overcome. It still makes sense to post a price on the gram bundle and let the buyer decide whether he wants to purchase or not. But again, his valuation function is no longer a sum of independent random variables, so maybe it's not necessarily going to concentrate well. So somehow we have to overcome this as well. Okay, and the last thing is that to guarantee optimality, now lottery systems must offer distributions over all possible subsets of items. Because the buyer's not additive, it's not enough just to consider probability vectors over the different items. So somehow we also have to accommodate this. Okay, still, we'd like to sell separately or together because of the nice robustness properties, but we have to accommodate these new challenges. And basically, there's like no prior work in this problem. What we do know, we have some impossibility results. So we know that if you relax this independence assumption, then it becomes NP hard to maximize revenue exactly. And this was known from earlier work of Dobzhinsky, Fu, and Kleinberg. And we also know that it's NP hard to get any polynomial approximation. So like any reasonable approximation you can't get if you don't have this independence assumption. Was that a signal to stop or 5 minutes?
5 minutes.
Okay. Okay, but still, the punchline I hinted at earlier is it's still the case, even in this more general model, that the better of selling separately and selling together gets you a constant factor approximation to the optimal revenue, as long as the distribution is subadditive with independent items. Okay, and the proof actually follows the same outline as what I showed you earlier in the talk, except there's each step has some new challenges. Basically what I want to do is I'm going to highlight what these challenges are, and then I'm just going to wrap up with a conclusion slide. Okay, so in the first step, we said we had to prove something like a core decomposition lemma. Okay, and we saw that one key ingredient in the proof was this marginal mechanism lemma that said we want to turn a mechanism that sells items in S union T into one that just sells items in T. And how we're going to do that is we're just going to pay the buyer exactly their value for what the items in S would have been. Okay, so now the catch is that if the buyer is subadditive, then it doesn't make sense to just say, oh, I know your value for the items in S, because it depends on exactly what set of items in T they got. Okay, so you can't just go through this kind of argument directly, but what we are able to do is we prove something that we call an approximate marginal mechanism lemma, and basically the marginal mechanism lemma holds approximately for subadditive buyers. Okay, so again, I know that's not a lot of detail, but that's at a high level, one of the techniques that goes on here. Okay, second is we still have to bound, once we have the core decomposition lemma, we have to bound the revenue of the tail. And again, we have this challenge that it's NP hard even to figure out which items the buyer is purchasing. Right? So some very weird structure could be seen in terms of what items a buyer chooses to purchase at different prices. And it turns out, okay, so there is at least one case where it's easy to figure out what items the buyer purchases, and that's if he's only willing to purchase exactly one item, then the buyer will purchase that item and nothing else. Okay, and surprisingly, it turns out that only analyzing revenue from these cases suffices to prove this same bound. Okay, so it's not clear that this should be the case, but it turns out that it is the case. Okay, now the last step is, again, we have to bound the welfare of the core using the better of Srev and Brev. Okay, and just to remind you before, our earlier proof used the fact that Srev is additive across the items, and we also use the fact that variance is additive across sums of independent random variables. Okay, and for subadditive buyers, just both of these are no longer true. Okay, so how we overcome this is, again, similarly to how we resolve the issue up here, only counting revenue from cases where the buyer wants to purchase exactly one item overcomes this first difficulty. And in order to deal with the concentration, it turns out that we can just invoke a stronger concentration bound due to work of Shechtman. And it turns out that it applies exactly in the model that we need it to apply to get the result. Okay, so I know that that's really high level, but these three things together culminate in the main theorem, which is that for any distribution over subadditive valuations with independent items, the better of Srev and Brev gets you a constant factor approximation.
So what is Srev here? How do you compute it?
Okay, so what we say for Srev, it turns out that this only, so I have some pricing scheme, and for this pricing scheme, I am only counting revenue in instances where the buyer is willing to purchase exactly one item. Does that make sense?
The optimal price, so, and then that's Meyerson then, or not?
No. So it's going to be higher. It's going to be Meyerson that sells with, at most, some probability. So basically, for this Srev, the prices have to be really, really high so that most of the time you're only buying one item, and then optimal subject to being at least so high.
You can approximately find those prices?
And you can find these prices exactly. Yeah. Okay. So just to recap, the first theorem I showed you is that when the buyer is additive and the items are independent, that the better of selling separately and together gets you a 6 approximation. Second thing I showed you is that if the buyer is subadditive but the items are independent, then the better of Srev and Brev gets you a constant factor approximation. And both proofs use this Quartal Decomposition framework to do it. Okay, so there has been some other recent work that followed up this first result by Bateni et al. And they showed how to extend this first theorem to a model of limited correlation. So we know that it doesn't hold with arbitrary correlation because we have this infinite gap example. But with some model of limited correlation, you can extend this, and I forget exactly what the constant factor is, but you lose another small constant factor by accommodating correlation. And second is that Aviad and I also were able to show how these results also imply bounds on this non-monotonicity phenomenon. Okay, so basically the idea is that Srev and Brev are monotone mechanisms in the sense that if you've restricted yourself to selling separately, and people like your items more, your revenue can only go up. Okay, so what that means is that better product distributions have at least 1/6 of the revenue of distributions that they stochastically dominate. So in particular, this means that if you go on an advertising campaign, you may hurt your revenue, but you're not going to hurt it more than a factor of 6. Okay, and for subadditive buyers, even though Srev is no longer a monotone mechanism, our analysis is, and it's basically because we're only counting revenue from the case where at most one item sells. And so this result extends there as well. And so I'll just put up, I think in this area, kind of the main open question is that following this work, basically we proposed 3 ways to generalize it. One is to non-additive buyers, and that was Aviad and myself. One was to buyers with limited correlation, and that was Bateni et al. And then one was to many buyers, and we just saw Yao talk about that earlier today. And somehow, all 3 of these papers use different techniques, and it doesn't seem to be trivial to combine even any 2 of them. But I think that kind of the central open question here is ideally to see just how far simple mechanisms can go. And that's all I have. Thanks for listening.
The marginal mechanismlemma in its exact version, does it extend at all beyond the additive case?
So if you are additive between S and T, then it extends. So like you can have crazy valuations within S and crazy valuations within T, but as long as you're separable across S and T, then it extends exactly. And I don't know, Noam and Sergio are here, I don't know if they know that it extends beyond that, but okay. So yeah, we don't know if it extends exactly beyond that.
Do you know if you can decompose into the revenues with the core and the tail with some factor?
Yes, so for a single buyer, that's actually the way it was stated in Lee and Yao's paper. So for a single buyer, you can decompose it into a worst constant factor times the revenue of the core plus the revenue of the tail. It turns out that the best way we know how to upper bound the revenue of the core is with the welfare of the core. So it made more sense to not lose the constant factor and just target it directly.
You said it's NP-hard for the buyer to optimize. So what's exactly the solution concept for computationally bounded buyers? Do you basically assume that they can do any crazy thing as long as they don't have any opportunity to buy a single item?
Yes. So I would say, so even if you get 0 revenue from buyers who face a tough decision, then this bound still holds. So basically, so as long as you have a model of buyer where if they have a trivial decision, they choose to buy the one item that they like, then this bound will hold, and they can do anything crazy in the other settings.
Okay, let's take further questions offline. Thank Mara again.